Okay, so quick review from last week. Okay, remember that we were talking about work energy theorem that says that work is a change in energy. Okay, and that the first step in solving any work energy theorem problem is to identify what type of energy is changing, be it potential or kinetic. How do I tell if it's potential? If height is involved. So something is being lifted or lowered, okay, then work is being done and changing the potential energy. How do I know if it's kinetic? Changing speed, right. Okay, so if there's an acceleration, be it positive or negative, okay, then there's work being done that is changing the kinetic energy, so that's the things we got to watch for. So if we have a situation where work is changing the potential energy, okay, then we would say this, and we would say that work equals our final potential energy minus our initial potential energy. We may have to expand the work out to this, force times distance. Okay, and then we would expand out to this as well, mghf minus mghi, and then from there it's a matter of algebra. I have to solve for whatever it is the question is asking me to solve for. It might be force, it might be distance, or one of the two heights. Okay, that would be all you would ever be asked to solve for. If the question involved a change in kinetic energy, okay, then we would expand to this. Work is going to be our final kinetic energy, EKF minus EKI, okay, and then we might expand out to this, force times distance equals 1/2 mdf squared minus 1/2 mdi squared, and then again, it's just a matter of algebra from there. I need to solve for whatever it's wanting me to solve for. Could be force, could be distance, or one of the two speeds. Okay, everybody ringing a bell from last week? Okay, so are these questions very patterned? They are, right? Like the first three, if this was a 6-mark or even a 5-mark question, the first 3 marks are always this. Okay, write our givens, write our work as a change in whatever kind of energy, and set up work energy theorem. After that, it's algebra, manipulate, plug, solve. Okay, so it's always going to be patterned, right? Okay. Let's have you guys try question number 1 and see how much we remember here. Now this one does have a little bit of a change. Remember on this one I said, or actually on all of them I said, sometimes we may have to expand out to this. But sometimes we don't. Sometimes the question just asks for work. Kind of like this one. Just asks for work in the first part and then asks us to calculate force after that. Okay, so give you guys a few minutes to try that one, okay, and see how you do, and then we'll walk through it together. All right, so if we're starting this one out, okay, our givens are that we know the mass, but it's in grams. What do I need it in? Kilograms, because a joule is a kilogram meters squared per second squared. Okay, so I'm going to need this to be in kilograms, 0.200 kilograms. And it's launched from ground level, which means my initial height is 0 meters, and it reaches a height of 1,600 meters. That would be my final height. Okay, it wants to know how much work is done. Well, what kind of energy is changing in this? Potential energy is changing. So work equals a change in potential energy, which means I don't need the force times distance part for part A. Okay, I don't need it for part A. I'm only being asked to calculate the work, which only involves me calculating the change in potential energy. So m times g times hf minus m times g times hi. Do I need to do that part, the mghi part? No, because it's 0. Okay, when you're on the ground, you don't have any potential energy. So my work is equal to the final potential energy because that's how much I'll change the energy by. That's how much work I will have to do. Okay, so all I have to do is go 0.200 times 9.81 times 1,600 meters. so 0.2 times 9.81 times 1600. All right, so that's going to take 3,139.2 joules. Worth of work. Okay, so that's part A. Now that I know that, can I calculate how much force was used? I can, because the other way to calculate work is this, force times distance. Okay, now, what distance do I use here? What was the distance over which the force has to be exerted if this thing goes from 0 to 1,600 meters? In this case, wouldn't the distance also be the height? Okay, you're changing the potential energy. We went over this, but you guys probably forgot about it because we only went over it once. Okay, m times g calculates the force of gravity. And height is a vertical distance. So it's really, that formula is really just force times distance. That's why it comes up to joules when we use it. Okay, so all I have to do to calculate the force is divide the work by the distance, which is 1,600 meters, and I'll get the force. Okay, so that'll be 3,139.2 divided by 1,600 meters, okay, and that'll get me the force. All right, so 1.962 newtons. All right, everybody okay with that? All right. Is that one a little bit different than the ones we've done up till now? I mean, a little bit, right? It didn't set up with exactly the steps, at least in the order we've always done them. Still the same steps, okay? But I shuffled the order a little bit. And the reason I did that was just to see if you remember what the definition of work is. That work is a change in energy, okay? And that you can calculate work without having to use force times distance. Okay? You can calculate it with just a change in energy. All right? Okay. Let's see if you guys can do this one. We did a lot like this one last week, and this one is much more typical. So on this one here, our givens are that we have a marble with a mass of 0.135 kilograms. Okay, and it's shot across a level floor. If it's level, that means the height's not changing. Okay, a rubber band is stretched using 300 newtons worth of force, and it accelerates the marble from rest to 18 meters per second. All right, how far was the rubber band stretched would be the distance over which the force of 300 newtons was exerted. Okay, in this question, what kind of energy is being changed? Kinetic, right? The speed is changing. All right, so then we'll say that force times distance, I know I'm going to have to expand that out for this question because I'm given force and asked for distance, okay, is going to equal my final kinetic energy minus my initial kinetic energy, but I know from my givens that that's 0 because it wasn't moving. And so I'll set up force times distance equals 1/2 mvf squared, and I'm looking for d. So I would manipulate to get d by itself by dividing both sides by f. So that'll be 1/2 times 0.135 times 18 squared divided by 300. So 0.5 times 0.135 times 18 squared and divided by 300. All right, so we are getting a distance there was stretched 0.073 meters. Okay, everybody all right with that one? So that's like 7.3 centimeters. That far. Okay, questions there? Okay, so this one is going to involve a different, I mean, all the steps are still the same, but in this case, our initial energy is not 0. We haven't, I think we've done like maybe 1 or 2 like this thus far, so that's why I put this question on here, because it's going to make us do a little bit different algebra. Algebra we haven't really done a lot of yet. Okay, so see how you do with this. Just in walking around, I'm seeing people kind of stuck at the same step. So I just want to kind of get to that step and then see if you guys can get it from there. All right, so obviously our givens are, we know the mass, 75 kilograms. Okay, we know the force, 225 newtons. Okay, and we know the distance is 10 meters. We know their initial speed is 14 meters per second, and we're looking for their final speed. All right, so from walking around, I've seen that everybody has identified this. Okay, that there was the kinetic energy that was changing. People got to this step here, okay, where they said that's EK final minus EK initial, and then everyone got to the next step as well, where they had the formulas expanded out. So I would actually say that you could start your manipulation at this step before you expand out to the formula. It doesn't mean you can't do it after you've expanded out to the formula, but I think sometimes it's easier to do the first part of the manipulation here. I'm looking for the final speed. That's part of that term. Yes? Okay. So if I want to get EKF by itself, what do I have to do with EKI? Add it to the other side. Okay, so remember, here's what this formula is saying. The change in energy equals final minus initial. So if I take the initial and I add it to the change, I should get the final. Agreed? Okay, so that's what I'm going to have here as my next step. Force times distance plus EK initial equals EK final. Right? Now I would say put in the formulas. If you put in the formulas before, okay, and you had this, you had force times distance equal 1/2 mvf squared minus 1/2 mvi squared, that's fine. Can I still move this all in one chunk? I can. Because in order of operations, I would do all the multiplying before I subtracted it from this one. So it's really just a number. It's like x. This is like y minus x. So I'm just going to take x and move it over to the other side by adding it. Okay? So once you get to this step here, expand it out and keep going. Okay? I'll give you guys a few more minutes to see if you can get that done now. Okay? Okay, let's have a look at the rest of this. So now that I've got this set up, I want to expand it out a little bit more, okay, by putting in the formulas for everything. So I'm going to have force times distance plus 1/2 mvi squared equals 1/2 mvf squared. Okay, now what I'm looking for is vf. Right? So what do I have to do with the half and the m to get vf by itself? Divide it over to the other side. Okay, so that solves for vf squared. I just want vf. So what do I need to do with this whole thing? Square root it. Okay, now I'm solving for vf. That's about as tricky as the algebra will ever get for a work energy theorem question. Okay, you didn't have 0 for your initial, so you actually had to do some adding and subtracting as well. All right, so when I plug all this in, I'm going to have 225 newtons times 10 meters plus 1/2 times 75 kilograms times 14 squared divided by 1/2 times 75 kilograms. Right? When I punch that into my calculator, I'm not going to do that all in one step. Okay, you can if you want, but I'm not going to. Okay, I'm going to go 225 times 10. Okay, and then I'm going to add to that 0.5 times 75 times 14 squared. And then I'm going to divide that by 0.5 times 75, which I put in brackets so that it does it in the order I want. Okay, so that is VF squared. I need just VF, so I need to take the square root of that number, which is 16 meters per second. Okay, so they accelerated from 14 to 16 over the last 10 meters. Okay, everybody all right with that? Okay, like I said, that's as tricky, algebraically speaking, as a question would get. Okay? The understanding part, from what I saw walking around, nobody had any problem understanding what was happening in the question, but we've never done any algebra that involved yet. Okay, so that was a little bit different for that one. All right, it's 9:14. I'm going to give you about a 5-minute break here, and then we're going to move on to some other ones here. Okay, so we are looking for the height an arrow will reach if it is fired straight up in the air from the ground using 300 newtons of force while being pulled back 0.75 meters. So somebody was laying on the ground, okay, pulled back a bow, okay, with an arrow in it, and then fired it. Okay, you want to see how high that arrow will go if it started from the ground. Okay, so we know the mass. Okay, as one of our givens, 0.09 kilograms, so it's 9 grams. Okay, it's 90 grams. Fired straight up in the air from the ground, so we know that HI is 0 meters. Okay, we know the force is 300 newtons, and we know the distance is 0.75 meters, and we're looking for the final height. Okay, so in this question, the potential energy is changing because it's only talking about height. Okay, and so then we can go force times distance equals m times g times h final minus m times g times h initial, which is 0 because we start on the ground. All right, so now it's just a matter of manipulating to get hf. So that means divide both sides by m times g. Okay, and then we plug in our numbers. So 300 times 0.75 divided by 0.09 times 9.81. Okay, so it's going to reach a height of 255 meters. Okay, 254.8. Okay, 254.8 meters. Okay, so on a question like that, if that was on a test, and honestly, last year I think I put a question, and instead of a bow and arrow, it was a catapult. Is it the same question? Yeah. Okay, instead of an arrow, it was a rock, because obviously catapults don't shoot arrows. Okay, so 1 mark here, 1 mark there, 1 mark there, 1 mark for manipulating, 1 mark for plugging in, 1 mark for your answer. Okay, that's what you would get. So is it worth your while to show all your work? Absolutely, especially the first 3 things. Okay, because you really, like, those are always the same. Okay, so always show them. You know what, give that one a try. Maybe it works a lot like the one we did. Seems like poor teaching to put 2 questions that are so much the same in a row. Now, I will warn you of one thing on this question, okay? Because I've had people do this with this question in the past. They write down 14 meters and they go, done! Is the building 14 meters tall? It is not. 14 meters is my initial height. Okay, we're going higher than that. We're starting at 14 meters. Okay, then we're doing 6,000 joules worth of work after that. Okay, so another 6,000 joules worth of work after that to get to the new height. Okay, what you're looking for is the top of the building, the new height. Okay, So on this one here, okay, we know the work this time, which actually, ironically, saves us work if we know it, okay? Because then we don't have to do force times distance. We already have the number, okay? We know the mass, 500 kilograms, okay? We know the initial height is 14 meters, and we're looking for the final height, okay? So obviously if height's involved, we're talking about a change in potential energy. So that means that work equals our final potential energy minus our initial potential energy. And on this one, we have both. Okay, the initial isn't 0 this time. So if I want to find the final height, which is part of EP final, what do I have to do with EP initial? Like before I plug in my MGH, what do I need to do with this term here? Move it to the other side. What's the opposite of subtracting? Adding, right? So I add it to the other side. So I'm going to have work plus my initial potential energy. So the change in energy plus my initial energy should give me my final energy. Okay? Now I can expand this out again. So this is a lot like the one we did that had with the sprinter, where they didn't start at 0. Okay? Except this one's potential and that one was kinetic. All right, so I'm going to take my work and add, whoop, not equals, plus m times g times h initial equals m times g times h final. So I'm looking for h final. What do I have to do with this mg? Divide it over to the other side. All right, that's going to solve for HF. That is the second most complex algebra you will ever have to do with a work energy theorem question. The most complex being the kinetic energy example we did with the sprinter, where you added in a square root sign. Okay, so when I'm plugging in my numbers here, 6,000 joules plus 500 times 9.81 times 14 meters divided by 500 times 9.81. Okay, so 6,000 plus 500 times 9.81 times 14 divided by 500 times 9.81. Okay, so it only goes another 1.5 meters. That's a very short floor. Okay, its final height is going to be 15.2 meters. What happens when Coder makes up a question on the fly and doesn't check it? That's not a very logical answer. Okay. All right, questions on how that one worked? Okay, so we did one like this last week, okay, where we got the ball being rolled up the ramp. The key words here are that it's being rolled at a constant speed. So all that's happening is we're going from here, so we got the ball here, and we're going to here. So this is something that we haven't really talked about very much, but sometimes, especially if you're a visual person, it helps to draw a picture. Okay, like for that last question, we could have drawn a picture of a building and drawn the 14th floor and the top floor and figured out what it was. If that helps you, go ahead and do it. Okay, there's absolutely nothing wrong with drawing a picture as part of a problem. Okay, so in this one here, I'm starting at the bottom. I'm pushing at 22 meters up the ramp. Okay, and I know that when I get to the top of the ramp, I will be 8.2 meters vertically higher than I was at the bottom of the ramp. We are looking for the force that was used to roll it up the ramp. Okay, so the challenge here, first off, what kind of energy is changing? Potential energy, because it's a constant speed. The second challenge, you have two things here that are in meters. One of them is the distance, and the other one is the height. Is it fairly straightforward to tell the difference? Which one's the height? Okay, the way you tell the difference, guys, is you have to go to the context of the question. The force was not exerted over this distance. The ball wasn't lifted. It was rolled up. Okay, so you pushed it 22 meters in order to get it 8.2 meters higher. Okay, all right, see if you can calculate the force on that one. Okay, so on this one here, okay, those are part of our givens. The other given is the mass, 1.2 kilograms. Okay, we know that the work being done here is changing the potential energy. Right, so we're going to have force times distance equals m times g times h final minus m times g times h initial. But since we started at the bottom of the ramp, there isn't any initial potential energy. Right, all we're going to have to do here is solve for force. Okay, so we're going to divide both sides by d, like so, and then plug in our numbers here. So force is going to equal 1.2 times 9.81 times 8.2 divided by 22, and that'll get us our force. So 1.2 times 9.81 times 8.2 divided by 22. All right, so 4.4 newtons worth of force was what was used. Okay, I think that was the unit exam question pre-COVID. Okay, so I've definitely used a question like that on a unit exam in the past. All right, how are we feeling about this? Okay, are we starting to get the pattern here? Okay. So here's the plan going forward. We have one major concept left and one very minor concept left in this unit. Okay? The law of conservation of energy is the major concept, efficiency is the minor concept. Efficiency takes us less than one class. Okay? Law of conservation of energy takes us several classes, and we have a lab. Right? So we have that to do before the 20. Okay? So there's a bit of work yet. So starting tomorrow, we'll probably start the law of conservation of energy. Okay, work on that, get our lab done either Thursday or Monday. Okay, I'll do the unit exam review on Friday of this week. Okay, we will probably have covered efficiency by then. If not, we'll cover it on the Monday. Okay, but it's pretty straightforward. Right. I would suggest that if you're struggling with any of this stuff, the number one thing for these questions is just practice. Okay, the more you practice it, the better at it you'll get. So doing mold equation calculations, the only way to get good at it is to practice. Okay, but come in and see me if you're struggling. Okay, lunch, nighttime, okay, after school, before school. Okay, come in and see me for some help. Okay, there's no shame in doing that. So make sure you come in and do that. You're not bothering me if you do. Okay. And then, like I say, we'll move on to conservation of energy, which is similar to this. There's a fair amount of algebra. Okay. But it's not any more difficult than this is. In fact, it might be a little bit easier. So there's that stuff left to do before the 20th. All right. I think I want you guys to do a couple more of these. I think I have a couple more in here. I do. Okay. All right. So this one here, you're looking for mass. We haven't done one where we look for mass for quite some time. So, okay, bobsled team is exerting a force of 800 newtons on a bobsled over a 15-meter distance. Bobsled accelerates from rest to 9.5 meters per second. You're looking for the mass of the sled on this one. Okay, let's have a look at this one. So we know the force on this one is 800 newtons. Okay, we know the distance is 15 meters. We know that the initial speed is 0 meters per second. We know the final speed is 9.5 meters per second. Right? So we're looking for the mass of the sled. In this one, it is the kinetic energy that is being changed by the work. All right? So that's going to mean force times distance equals 1/2 mvf squared minus 0. Okay, there's no initial kinetic energy because it tells us it's starting from rest. So all I have to do is isolate m. I do that, I divide both sides by 1/2 of Vf squared. Plug in and solve. Okay, that leaves mass over there by itself. So I take my 800 and multiply it by 15 meters, okay, and I divide that by 1/2 times 9.5 squared. Okay, so the mass of the sled is 266 kilograms, which is really heavy. It's like 500 pounds, more than 500 pounds. That's probably not the greatest.
What's got people in it?
Well, maybe there's a couple of people in it. We'll say that that's it. Good call. Okay. Because it's a 4-man bobsled team, and there's already 2 people in the sled, and it's just the last 2 guys pushing. Because otherwise, that's really heavy. Okay. All right. You have a quiz tomorrow. What do you suppose it will be on? This, yeah, definitely. 2 questions. Probably 1 potential, 1 kinetic, I would think. Okay, so make sure you try that tonight. Reminder that your lab reports for the work lab are due on Wednesday. Make sure you have those done. If you want me to look it over, pop in at lunch or at nighttime. Okay, and I'd be happy to do that.